This quick video is a follow-up to the Journey to the Center of the Earth video that you just watched. And I wanted to make note that the person that discovered the inner core by analyzing seismic waves was actually a female geophysicist back in the 1930s. Her name was Inga Lehman, and she is credited with discovering the inner core. Pretty amazing because there were not a lot of female geophysicists back then. So I've asked you to look at pages 37 and 38 in your lecture tutorial. So let's look at these together. The first part asks you to interpret the size of Earth's outer core based on the presence or absence of S waves. So remember that P waves travel through solids, liquids, and gases, but S waves only travel through solids. So the outer core, if it's liquid, is going to stop the transmission of S waves. Another thing to remember is the order in which these waves arrive to a seismic station. First, the P wave arrives. It's the fastest, P for primary. Then the S wave arrives, the secondary waves. And finally, the surface waves, which are the slowest but the most damaging. So on the diagram below, we're going to have to remember this picture right here because we're going to be looking at whether or not S waves have arrived at the various stations. And the idea is that if the S waves didn't arrive at the station, they must have been stopped by something that was liquid. First part asks you to circle the S waves in each seismic station. These have been done for you already here, here, and here. So notice that we have a little squiggle, that's the P wave, a second squiggle, that's the S wave, and then a large third squiggle, that's the surface waves. And again, we're concentrating on the S waves. So these three have been indicated. There's another one right here, but there isn't one here. We have a P and surface. We have no S wave here. Same with down here where they've actually indicated that. Let's go in the other direction. Here's an S wave. Here's an S wave. Here's an S wave, and that's it. There are no more S waves in the rest of these seismic recordings. It now asks you to draw an arrow to represent the path of the S wave from the earthquake to each of the stations that did record an S wave, and some have been done. So these first three have been done for you. Then we can add an arrow from the earthquake epicenter to this station, but not to this station because this station did not receive an S wave. Coming over here, we can go to each of these three stations. Those are all the places where the S waves made it through the earth and went to the station. Now, I mentioned to you in a previous video that the earthquake waves actually sort of curve as they go down and up, they bend. Don't worry about that. We're just simplifying this with straight lines. Based on the pattern, what is the phase of the outer core? Well, undoubtedly it must be liquid, because it's not passing through any of this region, and that's where we believe the outer core is. Question 4 says, draw a circle to show the size of the outer core on the diagram using the distribution of the S waves to help you. So what we need to do is draw a core in here that has the correct diameter so that S waves are not traveling through the core, but they're traveling through the mantle outside of the core. And this is an approximate example of what you should draw, something like this, so that the S waves traveled through this point, but they didn't travel to the next station because they were stopped by the liquid outer core. And remember, this is the core mantle boundary that I'm drawing in green here. So the mantle is solid and the core is liquid, and that is why these S waves are not penetrating through this region. It then says that the mantle is the layer between the outer core and the crust, and based on the S wave patterns, what is the phase of the mantle? Let's go back and take a look. Well, the S waves are traveling through the mantle, which is this white region here. So the mantle must be mostly solid. Now we're going to look at hypothetical planets that have had P and S wave measurements. We haven't been able to measure any quakes on any other planets, although we did recently send the first seismometer to Mars to try to measure Mars quakes. And one of the reasons we're trying to measure Mars quakes is not so much because we think Mars has plate tectonics, but because we might be able to determine something about Mars's interior through the exact same process we're doing here with P wave and S waves. Okay, so what size molten core does this planet have? So we first want to draw our S wave pathways, and that's it. None of these other stations have received an S wave. So that suggests that the core, the molten core, is quite large in this particular example. Let's look at this planet. Again, we'll draw arrows showing the propagation of the S waves. And in this case, they seem to go through the entire planet. So the conclusion is that there is no liquid core inside of this particular planet. So I hope this helps you understand how we've been able to determine not only the size of the outer core, but the fact that it is liquid. This is the end of our incredibly fast week of earthquakes, faults, folds, and now we are going to start a brand new unit on minerals. Eventually we'll get to rocks, and this will pretty much be the rest of the semester.